Chapter 1. Database Design. A solid database design is the foundation of effective SQL. Poor design choices, such as incorrect data types or flawed constraints, lead to complex and inefficient queries. This chapter emphasizes thinking in terms of sets of data, as SQL is designed around this mathematical concept, rather than the files and records of traditional programming. Key concepts in this chapter include schema and table creation. The create schema statement is the standard way to define an entire database structure at once, though many products have their own specific tools. A schema consists of tables, views, and constraints that define the data structure and rules. Manipulating tables. The core commands for managing tables are create table, drop table, and alter table. It's important to use meaningful, consistent names for tables and columns, e.g., plural nouns for tables like employees and singular nouns for columns like employee name. Column definitions and constraints. When defining a column, you can specify a default value to be used when a value isn't provided during an insert. Constraints like not null, unique, primary key, and check are crucial for ensuring data integrity. Check constraints are particularly powerful for enforcing complex business rules. Referential integrity. The references clause, along with onUpdate and onDelete actions like cascade, set null, set default, helps maintain consistency between related tables. Generating keys. While many databases offer auto-incrementing identity columns or GUIDs for primary keys, these can have drawbacks in terms of portability and adherence to relational principles. The book discusses pure SQL methods for generating unique sequential numbers. Modeling hierarchies. The chapter briefly introduces how to model hierarchical data, such as organizational charts or product categories, using SQL's data definition language, setting the stage for more advanced techniques later in the book. Chapter 2. Normalization. Normalization is the process of organizing columns and tables in a relational database to minimize data redundancy. The goal is to ensure that facts are stored in only one place, which helps prevent data anomalies, errors that can occur when you insert, update, or delete data. The chapter explains the different normal forms, which are a series of guidelines for database design. First normal form, 1N, this is the most basic level. It requires that a table have no repeating groups. Every column must hold a single atomic value. For example, instead of having child 1, child 2, child 3 columns, you should have a separate children's table. Second normal form, 2NF. A table is in 2NF if it is in 1NF and every non-key attribute is fully dependent on the entire primary key. This applies to tables with composite keys, keys made of more than one column. Third normal form, 3NF. This is the most common and important level of normalization for many applications. It requires that a table be in 2NF and that all attributes are dependent only on the primary key, not on other non-key attributes. This eliminates transitive dependencies. Higher normal forms, BCNF, 4NF, 5NF, these address more subtle and complex data redundancies. Boyce-Codd normal form, BCNF, is a stricter version of 3NF. Fourth normal form, 4NF, deals with multi-valued dependencies, where one piece of information in a table implies multiple pieces of other information. Fifth normal form, 5NF, addresses join projection anomalies, which can occur when a table representing a many-to-many relationship is broken down incorrectly. Denormalization. Sometimes, for performance reasons, a database is intentionally designed to be in a lower normal form. This is called denormalization. While it can speed up queries by reducing the need for joins, it should be done carefully as it reintroduces the risk of data anomalies. This is more common in data warehouses than in transactional systems. Chapter 3. Numeric Data in SQL. SQL provides a variety of numeric data types, broadly categorized as exact and approximate. Exact numeric types. These include integer, small int, big int, numeric, and decimal. They store numbers with precise precision and scale. For example, decimal 8,2 can store a number like 123,566.78. Approximate numeric types. These include float, real, and double precision. They are used for scientific and engineering calculations where absolute precision is less critical than a wide range of values. They are often based on the IEEE 754 standard for floating point numbers. The chapter also discusses bit, byte, and Boolean types. The author advises against using these low-level, hardware-specific types in SQL because they violate the principle of data abstraction and are not portable. Numeric type conversion. When converting between numeric types, SQL may need to round or truncate values. The rules for this can vary between database systems, so it's important to be aware of how your specific product handles it. The cast function is the standard way to perform explicit type conversions. Arithmetic and nulls. Any arithmetic operation involving a null value results in null. This is a key concept to remember to avoid unexpected results in calculations. Nullif and coalesce. These are useful functions for handling nulls. Nullif v1, v2 returns null if v1 and v2 are equal, otherwise it returns v1. Coalesce v1, v2, etc. returns the first non-null value in a list of expressions. This is very handy for providing a default value in calculations. For example, coalesce commission, 0. Chapter 4. Temporal data types in SQL. Working with dates and times in SQL can be complex due to the irregularities of the calendar, leap years, different month lengths, etc. SQL 92 introduced standard temporal data types to address this. Temporal data types. Date stores year, month, and day. Time stores hour, minute, and second. Timestamp stores both date and time, often with fractional seconds. Interval represents a duration of time, e.g., 3 days, 5 hours, not a specific point in time. Calendar standards. The chapter highlights the importance of using a standard date format like the ISO 8601 standard YYY-MM-DD to avoid ambiguity, especially in international applications. It also touches on the complexities of historical calendars and time zones. Temporal data models. A key concept is the valid time state table, which tracks when a piece of information was true in the real world. This is often done using from-date and to-date columns to represent a period of validity. Temporal duplicates. The chapter discusses different kinds of duplicate data in a temporal context, such as non-sequenced duplicates, exact copies of rows, value-equivalent duplicates, same data, different timestamps, and sequenced duplicates, overlapping periods of validity for the same data. Transaction time. This is another dimension of time that records when data was stored or changed in the database itself. A table that tracks both valid time and transaction time is called a bitemporal table. Modifying temporal data. The chapter explains how to perform insertions, updates, and deletions on temporal tables. For example, a logical delete on a valid time table is often implemented as an update that sets the to date of the current time to the current time, effectively ending its period of validity. Chapter 5. Character data types in SQL. SQL provides several data types for storing character strings. Char n, a fixed-length string of n characters. Varchar n, a variable-length string with a maximum length of n characters. Nchar n, and nvarchar-n, national character versions for storing Unicode characters, which support a much wider range of international alphabets. The chapter covers common issues and functions related to string manipulation. String comparison. SQL's rules for comparing strings can be tricky. For example, when comparing strings of unequal length, the shorter string is padded with spaces on the right. This means Smith and Smith space are considered equal. However, the like predicate does not do this padding. Case sensitivity. Whether string comparisons are case-sensitive can vary. The standard functions upper and lower are useful for performing case-insensitive comparisons. Standard string functions. Substring extracts a portion of a string. Trim removes leading, trailing, or both spaces or other characters from a string. Char length returns the length of a string. Position finds the starting position of a substring within another string. Phonetic matching. The chapter discusses algorithms for finding names that sound alike but are spelled differently. SoundX, a classic algorithm that produces a 4-character code representing the phonetic sound of a name. Metaphone and NYSIS, more advanced and accurate phonetic matching algorithms. Cutter tables, a library science technique for encoding author names into a fixed-length code that preserves alphabetical order. Chapter 6. NULLs, Missing Data in SQL. Null is a special marker in SQL that represents a missing, unknown, or inapplicable value. It is not a value itself, but a placeholder. Handling nulls correctly is one of the most challenging aspects of SQL. 3-valued logic. Because of null, SQL uses a 3-valued logic system: true, false, and unknown. Any comparison involving a null other than is null results in unknown. The where clause of a query only accepts rows that evaluate to true. Is null predicate. The only way to test for a null is what the is null or is not null predicate. You cannot use equals null. Nulls in subqueries. Nulls in the result of a subquery can lead to unexpected behavior, especially with the not in predicate. If the subquery returns even one null, the not in condition will never be true. Nulls and aggregate functions. Most aggregate functions like sum, avg, max, men, ignore nulls in their calculations. Count star, is the exception. It counts all rows regardless of their content. Design advice for nulls. Use the not null constraint whenever possible to avoid the complexities of nulls. Primary key columns cannot be null. Be very careful with nulls in foreign key columns. Instead of null, consider using a special value like 0 or n-a if the meaning is clear and it simplifies your code. However, this is not always appropriate. Multiple null values. The chapter briefly touches on the theoretical idea of having different types of nulls, e.g., one for unknown and another for not applicable, but standard SQL only has one general-purpose null. Chapter 7. Multiple column data elements. Some data elements are naturally composed of multiple parts that should be stored in separate columns but treated as a single unit. Distance functions. An example is geographic coordinates, latitude and longitude. The chapter provides a function to calculate the distance between 2 points on the globe given their coordinates. IP addresses. An IP address can be stored in several ways. As a single varchar 15 string, this is simple and human-readable but can be inefficient for searching and requires parsing. As a single integer, this is very efficient for storage and searching but is not human-readable and requires functions to convert to and from the dotted octet format. As 4 separate small int or tiny int columns, this is often a good compromise, offering reasonable storage efficiency, easy searching on individual octets, and better readability. Currency and units. When dealing with money or other measurements, it's essential to store both the amount and the unit, example USD, EU, kilogram, LBS, in separate columns. The chapter also discusses the specific rules for converting between currencies, especially involving the euro. Social Security numbers. The chapter provides a detailed breakdown of the structure of U.S. Social Security numbers, explaining how the different parts, area, group, serial, are assigned. Rational numbers. A rational number, a fraction, can be modeled in SQL by storing the numerator and denominator in two separate integer columns. This requires user-defined functions to perform arithmetic on these fractions. Chapter 8. Table Operations. This chapter covers the three fundamental data manipulation language (DML) statements for modifying data in tables: delete, insert, and update. Delete from statement. This statement removes one or more rows from a table. If you omit the where clause, all rows in the table will be deleted. Be careful. The where clause can include complex conditions and subqueries, even referencing other tables. When deleting rows based on conditions within the same table, e.g., deleting employees with below-average salaries, SQL conceptually evaluates the condition against the entire table first before deleting any rows. This avoids the disappearing data problem that could occur with a row-by-row approach. Insert into statement. This is the only way to add new data to a table. You can insert a single row using the values clause. You can insert multiple rows by providing the results of a select query. The default values clause can be used to insert a row with all default values. Update statement. This statement modifies the values in existing rows. The set clause specifies which columns to change and their new values. The assignments in the set clause happen in parallel, which allows for tricks like swapping the values of two columns in a single statement. Like delete, if you omit the where clause, all rows in the table will be updated. You can use subqueries in the set clause to update a table with values from another table, e.g., posting daily sales totals to a customer's account balance. The case expression is extremely useful in update statements for applying conditional logic, which can often combine several separate update statements into a single, more efficient one. Merge statement. A newer feature in SQL from SQL 99, the merge statement, sometimes called upsert, combines insert and update operations into a single statement. It matches rows from a source table to a target table. If a match is found, it performs an update, and if not, it performs an insert. Chapter 9. Comparison or Theta operators. This chapter delves into the operators used for comparing values in SQL, often called theta operators in relational theory. These include equal, not equal, less than, greater than, less than or equal to, and greater than or equal to. Data type conversion. When comparing values of different numeric types, SQL will promote one value to the higher type before performing the comparison. For example, when comparing an integer and a float, the integer will be converted to a float. String comparison. When comparing character strings of unequal length, the shorter string is padded with spaces on the right to make the lengths equal. Temporal comparison. You can only compare dates with other dates or timestamps, and times with other times or timestamps. You cannot directly compare a date and a time. Row comparisons. Standard SQL allows you to compare entire rows, not just single scalar values. For example, you can write city, state equals New York, NY. The comparison is done lexicographically, from left to right, similar to how words are alphabetized. This is particularly useful for working with composite keys. Chapter 10. Valued Predicates. This chapter covers a set of special predicates that test for logical or null values. Is null predicate? As discussed before, this is the only way to test for the presence of a null. Standard SQL extends this to work on entire rows. Row is null is true only if all the columns in the row are null. Is not, true, false, unknown predicate. This powerful predicate, introduced in SQL 92, allows you to explicitly test the result of a logical condition. Remember that in SQL's three-valued logic, a condition can result in true, false, or unknown. This predicate allows you to handle the unknown case directly. For example, where x greater than y is not false will be true if x greater than y is either true or unknown. This can simplify queries that would otherwise require complex OR conditions to handle nulls. Is not, normalized predicate. This is a specialized predicate for working with Unicode strings. Unicode allows a single character, like E, to be represented in different ways, e.g., as a single character or as a base letter E followed by a combining accent mark. This predicate checks if a string conforms to one of the standard Unicode normal forms. Chapter 11. Case Expressions. The case expression is one of the most powerful and versatile features in SQL. It provides a way to implement conditional logic directly within a query, similar to an if-then-else construct in other programming languages. Forms of case. Simple case. This form compares a single value against a series of other values. Example, case, gender, when M, then male, when F, then female, else unknown, end. Searched case. This is the more general form where each when clause contains its own logical condition. Example, case, when salary less than 50,000, then low. When salary greater than 50,000 and salary less than 100,000, then medium, else high, end. Else clause. If no when condition is met, the case expression returns the value in the else clause. If you omit the else clause, it defaults to else null. Coalesce and nullif. The chapter reiterates that these functions are actually shorthand for specific case expressions. Case with group by. Case expressions are extremely useful with aggregate functions. You can use them to create crosstab or pivot reports. For example, you can count the number of male and female employees in each department with a single group by query. Select deptnum, sum, case when gender equals M, then 1, else 0, end, as male count, sum, case when gender equals F, then 1, else 0, end, as female count, from employees, group by deptnum. Case in check constraints. Case can be used to implement complex logical rules, including logical implication, if A, then B, in check constraints to enforce data integrity. Chapter 12. Like predicate. The like predicate is used for simple string pattern matching. Wildcards. Underscore, underline, matches any single character. Percent, percent sign, matches any sequence of 0 or more characters. Escape clause. The escape clause allows you to specify a character that can be used to escape the special meaning of the wildcard characters. For example, like 104%, escape 4, would match a string that starts with the literal text 100%. Performance. Queries with a leading percent, e.g. like %sun, are often slow because they cannot use a standard index. It's more efficient to match from the beginning of the string whenever possible. Like versus equality. It's important to remember that like does not pad strings with spaces, unlike the equality, equal sign operator. similar to predicate, a newer, more powerful pattern matching predicate introduced in SQL 99. It supports a richer set of regular expression syntax, similar to what's found in tools like grep in Unix. This includes features like alternation, or, plus, and character classes, square brackets. Chapter 13. Between and overlaps predicates. These two predicates are used for checking if a value or a time period falls within a range. Between predicate. This predicate checks if a value falls within an inclusive range. X between y and z is equivalent to x greater than or equal to y and x less than or equal to z. It works with numeric, character, and temporal data types. If any of the values are null, the result will be unknown. Be careful with the inclusiveness of the endpoints, especially with continuous data like dates or money. Overlaps predicate. This predicate, part of the SQL standard but not widely implemented, is specifically for temporal data. It checks if two time periods overlap. A time period is defined by a start time and either an end time or a duration, interval. The standard defines that a period includes its start point but not its end point. The chapter provides a pure SQL workaround for checking if two date ranges overlap, where not underscore end date 1 less than start underscore 2 or start underscore 1 greater than end date 2. Chapter 14. The in predicate. The in predicate checks if a value is present in a list of values or in the results sec of a subquery. -in versus or. A query with multiple or conditions on the same column, e.g., where x equals 1, or x equals 2, or x equals 3, can often be rewritten more concisely and sometimes more efficiently using in, e.g., where x in 1, 2, 3. -in versus join. A query that uses in with a subquery can often be rewritten as a join, which may perform better, especially if the columns being joined are indexed. However, the join may produce duplicate rows that need to be handled with select distinct. -not in and nulls. This is a major gotcha in SQL. If the subquery in a not in predicate returns even a single null value, the entire not in condition will never evaluate to true for any row. The result will either be false or unknown. This is because x not in dash 1 null dash is equivalent to x less than 1 and x less than null and x less than null. And the x less than null part is always unknown. Because of this, it's often safer to use not exists instead of not in. Chapter 15. Exists predicate. The exists predicate is a powerful tool that tests for the existence of rows in a subquery. How it works. Exists subquery returns true if the subquery returns 1 or more rows and false if it returns 0 rows. It never returns unknown. Performance. Exists can be very efficient, especially with correlated subqueries, because the database can often use an index to check for the existence of a matching row and can stop searching as soon as it finds one. It doesn't need to build the full result set of the subquery. Exists versus in. As mentioned, not exists is often a safer and faster alternative to not in. Exists can also be used to rewrite in queries, often with better performance. Exists and joins. An exists query can often be flattened into an inner join. A not exists query can often be flattened into a left outer join with a where .is null clause. Universal quantification for all. Exists can be used to express the logical concept of for all. The statement, all salesmen are liars can be rephrased as there does not exist a salesman who is not a liar, which can then be implemented with not exists. Chapter 16. Quantified Subquery Predicates. These predicates extend the standard comparison operators equal, exclamation mark, less than, etc., to work with the result sets of subqueries. Any or some. X greater than any subquery is true if X is greater than at least one of the values returned by the subquery. Equal any is equivalent to in. All. X greater than all subquery is true if X is greater than every value returned by the subquery. Exclamation mark equal all. Handling nulls and empty sets. If the subquery returns an empty set, any is false, and all is true. The latter is often counterintuitive, but is based on the principles of formal logic. The statement, "I can beat up any pink elephant in this room," is true if there are no pink elephants. If the subquery returns nulls, the results of these predicates can become unknown. All versus extrema functions, max, min. X greater than all subquery is not always the same as X greater than equal to X greater than equal select max from because max ignores nulls while all does not. Unique predicate. Unique subquery is a special predicate that is true if the subquery returns no duplicate rows. Nulls are not considered equal to each other for this purpose. Chapter 17. The select statement. This chapter provides a deep dive into the select statement, the workhorse of SQL. Order of execution. The chapter explains the logical order in which the clauses of a select statement are processed. 1. From. The tables are joined to form a working set. 2. Where. Rows are filtered. 3. Group by. The remaining rows are grouped. 4. Having. The groups are filtered. 5. Select. The final columns are selected and expressions are calculated. 6. Order by. Part of a cursor. The final result set is sorted. Join syntax. The chapter contrasts the older comma-separated join syntax in the where clause with the modern explicit join syntax in the from clause, inner join, left outer join, etc. The modern syntax is generally preferred because it is clearer and more powerful. Outer joins. Left outer join keeps all rows from the left table even if there's no match in the right table. Right outer join keeps all rows from the right table. Full outer join keeps all rows from both tables. The chapter stresses that the order of outer joins matters. A left join B, left join C is not the same as A left join B, left join C. Union join. A little-known and rarely implemented join from the SQL standard that essentially creates a union of two tables without trying to match rows, padding with nulls where columns don't exist in the other table. Chapter 18. Views, Derived tables, Materialized tables, and Temporary tables. This chapter explores different ways to create virtual or temporary table-like structures in SQL. Views. A view is a stored query that can be treated like a table. It doesn't store data itself, it's a window onto the data in one or more base tables. Uses. Simplifying complex queries, providing a consistent interface to data, and implementing security by restricting access to certain rows or columns. Updatability. A view is only updatable, meaning you can use insert, update, or delete on it if it's based on a single table and meets several other strict criteria. With check option. This clause on a view ensures that any data modified through the view must still satisfy the view's where clause. Derived tables. These are like temporary views that exist only for the duration of a single query. They are defined directly in the from clause of a select statement, e.g., from select, from my derived table. Common Table Expressions, CTEs. Introduced in SQL 99, a CTE is a named derived table defined using a with clause at the beginning of a query. CTEs are very powerful because they can be referenced multiple times within the same query and can also be recursive, which is essential for working with hierarchical data. Temporary tables. These are actual tables that are created to hold intermediate results. Unlike views, they are materialized. They physically store data. The SQL standard defines global and local temporary tables that are automatically cleaned up at the end of a session or transaction, but many database systems have their own proprietary implementations. Chapter 19, Partitioning Data in Queries. This chapter focuses on techniques for dividing a set of data into meaningful subsets. Coverings and partitions. A partition divides a set into non-overlapping subsets. A covering allows the subsets to overlap. Most reports are based on partitions. Partitioning by ranges. A common task is to classify data based on where it falls in a range, e.g., assigning letter grades based on numeric scores. This is often done using the between predicate or by joining to an auxiliary table that defines the ranges. Relational division. This is one of the original relational algebra operations. It's used to answer questions like, find the pilots who can fly all of the planes in the hangar. The chapter presents several ways to implement this in SQL, including using not exists, counting, and except. The performance of these different methods can vary greatly between database systems. FIFO and LIFO subsets. The chapter provides SQL solutions for first-in, FIFO, and last-in, LIFO inventory valuation problems, which involve processing a set of transactions against a set of inventory blocks in a specific order. Chapter 20, Grouping Operations. This chapter expands on the group by clause and related concepts. Group by clause. This clause groups rows that have the same values in specified columns into summary rows. Each row in the result represents one group. Nulls in the grouping columns are all treated as a single group. Halving clause. The halving clause is used to filter the results of a group by query. It's like a where clause for groups. You can use aggregate functions in the halving clause, but not in the where clause. Multiple aggregation levels. The chapter explains how to create reports with multiple levels of subtotals, e.g., sales by salesman, then by district, then by region. While this can be done with a series of unioned queries, it's often better to use OLAP functions like rollup and cube if your database supports them. You can also achieve this by creating grouped views and joining them, or by using subqueries in the select list. Grouping on computed columns. Newer versions of SQL allow you to group by an expression or a computed column. In older versions, you can achieve the same result by using a derived table. Chapter 21, Aggregate Functions. Aggregate functions perform a calculation on a set of values and return a single value. Standard aggregates. Count star counts the total number of rows. Count expression counts the number of non-null values. Sum calculates the sum of a set of numeric values. AVG calculates the average. Min and max find the minimum and maximum values. These work on numeric, character, and temporal data. Distinct. All of these functions, except count star, can be used with the distinct keyword to perform the calculation only on the unique values in the set. Generalized extrema functions, top n. The chapter presents several complex SQL queries for solving the top n problem, e.g., find the 3 highest paid employees. This is a non-trivial problem in SQL, and the solutions often involve self-joins and correlated subqueries. Greatest and least. These functions, available in some database systems, find the greatest or least value from a list of columns in the same row, a horizontal max-min. Custom aggregates, list, PRD. The chapter shows how to simulate aggregate functions that don't exist in standard SQL, such as a list function to concatenate a column of strings into a single comma-separated string, a PRD product function to calculate the product of a column of numbers, often by using logarithms, exp, sum, ln of x. Chapter 22. Auxiliary tables. Auxiliary tables are helper tables that are not part of the core data model, but are used to simplify complex queries and calculations. Sequence table. A simple table containing a sequence of integers, 1, 2, 3, etc. This is incredibly useful for replacing loops and performing operations on each element of a list or string. Lookup tables. These tables are used to translate codes into more meaningful values, e.g. a state codes table to translate NY to New York. They can also be used to define ranges or hierarchies. The chapter advises against the one true lookup table, OTLT, anti-pattern, where all codes for the entire system are stored in a single table, as this leads to poor design and performance. Function tables. You can calculate the results of a complex mathematical function and store them in an auxiliary table. This allows you to perform the calculation by joining to the table instead of using complex formulas in your query. This is particularly useful for inverse functions or for performing interpolation. Global constants tables. A table with a single row can be used to store global constants for your application, e.g., pi, tax rates, conversion factors. Chapter 23. Statistics in SQL. While SQL is not a full-featured statistical language, it can be used to compute a variety of descriptive statistics. Mode. The most frequently occurring value in a set. This can be found with a group-by query and a halving clause that finds the group with the highest count. Median. The middle value in a sorted set. This is surprisingly difficult to calculate in pure SQL. The chapter presents several different methods, ranging from simple, but possibly inaccurate, to complex, but more robust, often involving self-joins and clever use of count function. Variance and standard deviation. These measure the spread or dispersion of a set of data. The chapter provides the formulas for calculating them in SQL. Cumulative statistics. These are running statistics, such as running totals and running differences. They are typically calculated using a self-join where you sum or compare all rows up to the current row. Rankings. The chapter shows how to assign a rank, first, second, third, etc., to each row based on a certain value, and how to handle ties. Crosstabs, pivot tables. A crosstab is a report that summarizes data in a grid format. The chapter demonstrates several techniques for creating crosstabs in SQL, with the most effective method often being the use of the case expression inside an aggregate function. Chapter 24. Regions, runs, gaps, sequences, and series. This chapter deals with analyzing sequential data, where the order of rows is important. Since SQL tables are inherently unordered, this requires a column that explicitly defines the sequence, e.g. a timestamp or a sequence number. Regions. A region is a contiguous block of rows with the same value. The chapter shows how to find regions of a certain size or the region with the maximum size. Runs and sequences. A sequence is a set of rows where the values are consecutive, e.g., 10, 11, 12. A run is a set of rows where the values are simply in increasing order, but not necessarily consecutive, e.g., 10, 15, 25. Gaps. The chapter provides queries for finding gaps in a sequence of numbers or in a series of time periods. This is a common problem in applications like scheduling or auditing. Coverings. A more advanced problem is to find the minimal set of intervals that covers a set of points. For example, given a set of overlapping time periods, what are the resulting contiguous periods of time? Chapter 25. Arrays in SQL. Standard SQL 92 does not support arrays, as they violate the principle of first normal form. However, they are a common feature in newer versions of SQL and in many vendor products. This chapter discusses how to model and work with array-like data in SQL. Arrays via named columns. A common but poor way to simulate an array is to have multiple columns like child 1, child 2, etc. This is inflexible and leads to many problems. Arrays via subscript columns. A much better approach is to model an array as a table with columns for the subscripts and a column for the value. For a 2D array or matrix, you would have columns for the row and column subscripts I, J, and a column for the element at that position. Matrix operations in SQL. Using the subscript column model, it's possible to perform matrix operations like addition, multiplication, and transposition using SQL queries, although it can be complex and inefficient. Flattening a table into an array. The chapter shows how to do the reverse operation, taking a normalized table, like sales data with one row per month, and flattening it into a single row with one column for each month, which is a common requirement for reports. Chapter 26. Set operations. This chapter covers the standard set theory operations as they apply to tables in SQL. Union and union all. Union combines the results of two queries and removes duplicate rows. Union all also combines the results but keeps all duplicate rows. Union all is generally much faster because it doesn't need to do the work of finding and removing duplicates. Intersect returns only the rows that appear in both of the query result sets. Like union, it removes duplicates. Intersect all is the multi-set version that respects the number of duplicates in each table. Except or minus in Oracle returns the rows from the first query that do not appear in the second query. Again, except removes duplicates, while except all is the multi-set version. Table equality and subsets. The chapter discusses how to test if one table is a subset of another or if two tables are equal. This is not as simple as it sounds due to the presence of nulls and duplicates. The book provides several methods for performing these comparisons using standard SQL constructs. Chapter 27. Subsets. This chapter presents techniques for extracting specific kinds of subsets from a table that go beyond a simple where clause. Every nth item. How to select every nth row from a table when there is a column defining the sequence. Picking random rows. SQL does not have a standard way to select a random sample of rows. The chapter discusses workarounds, which often involve using a vendor-specific random function, joining to a table of pre-generated random numbers, or using a hashing algorithm on a primary key. Contains operator. The chapter revisits the idea of a contains operator for checking if one set of rows is a subset of another, which existed in early experimental versions of SQL but is not in the standard. It shows how to implement this logic using not exists. Picking a representative subset. A more complex problem is to select a minimal subset of rows from a large table such that every distinct value in certain columns is represented at least once. The chapter presents both an iterative solution and a single query approximation for this problem. Chapter 28. Trees and Hierarchies in SQL. Representing and querying hierarchical data, like organizational charts or bills of materials, is a classic challenge in SQL. This chapter provides a high-level overview of the three main approaches. Adjacency list model. This is the most common method. The table has a column for the node and a column for its immediate parent. It's simple to implement, but very inefficient to query for things like finding all descendants of a node, as it requires recursive queries or loops. Path enumeration model. In this model, you store the entire path from the root to each node as a string, e.g. .a/c/d/. This makes finding all descendants or ancestors of a node very easy and fast using like predicates. However, updating the structure, especially near the root, can be very expensive as it requires updating the path strings for many nodes. Nested set model. This is a very powerful and elegant model for representing hierarchies in a set-oriented way. Each node is given two numbers, a left, LFT, and a right, RGT, which are assigned by traversing the tree. All descendants of a node will have LFT and RGT values that fall between the LFT and RGT values of the parent. This makes querying for subtrees, levels, and aggregations extremely efficient, often with a single self-join. However, inserting and deleting nodes is more complex as it requires renumbering a portion of the tree. Chapter 29, Temporal Queries. This chapter is a collection of practical techniques and puzzles related to temporal data. Personal calendars. The chapter emphasizes the utility of having a dedicated calendar auxiliary table. Such a table can store information about each date, such as whether it's a workday or a holiday, the day of the week, the fiscal quarter, etc. This often makes complex date-based queries much simpler and faster than trying to calculate this information on the fly. Time series analysis. The chapter presents SQL solutions for common time series problems, such as finding gaps in a time series, consolidating overlapping time periods into continuous periods, filling in missing start or end dates in a sequence of events. Julian dates. A Julian date is a continuous count of days since a specific starting point in the distant past. The chapter provides algorithms for converting between Gregorian dates and Julian dates. Weeks. The ISO 8601 standard has a definition for week numbers within a year, but it's not directly supported by SQL. The chapter discusses the ambiguities in defining a week and provides tricks for working with week-based data, such as sorting by the name of the weekday. The year 2000 problem. The chapter includes a historical look at the Y2K bug, explaining the different facets of the problem, odometer rollover, the special leap year rule for 2000, and how they relate to data representation and programming practices. Chapter 30. Graphs in SQL. A graph is a more general structure than a tree, allowing for multiple paths between nodes and for cycles. This chapter discusses how to model and query graph structures. Adjacency list model. This is the most common way to represent a general graph in SQL. The table stores the edges of the graph as pairs of begin node and end node. Acyclic graphs as nested sets. An acyclic, no cycles, graph can be converted into a tree or a forest of trees and then represented using the nested set model. This can make some queries more efficient. Finding paths. A key problem in graph theory is finding paths between nodes. The chapter shows how to do this using iterative SQL procedures or, more elegantly, with recursive common table expressions, CTEs, which are a feature of modern SQL. This includes finding all paths, the shortest path, or the path with the lowest cost, if the edges have weights. Points inside polygons. A related spatial problem is determining if a given point lies inside a polygon. The chapter provides a pure SQL algorithm for solving this problem for convex polygons. Chapter 31. OLAP in SQL. This chapter, contributed by Michael L. Gonzalez, provides an introduction to online analytical processing, OLAP, and how its concepts are being integrated into SQL. OLAP is used for business intelligence and data warehousing, and it focuses on summarizing and analyzing large volumes of data. OLTP versus OLAP. The chapter contrasts traditional online transaction processing (OLTP) systems with OLAP systems. OLTP is about short, frequent transactions on normalized data. OLAP is about complex queries on large, historical, often denormalized datasets. Star schema. This is the most common design pattern for data warehouses. It consists of a large central fact table containing numerical measures like sales amounts, surrounded by smaller dimension tables containing descriptive attributes like time, product, geography. OLAP functions in SQL. Modern SQL has incorporated many functions specifically for OLAP. Ranking functions. Ranking and dense rank assign a rank to each row within a group. Row number assigns a unique number to each row. Window functions. The over clause is a powerful feature that allows aggregate functions to be applied to a window of rows related to the current row, without collapsing the rows as a group by would. This is used for things like calculating moving averages and running totals. Grouping sets, rollup, and cube. These are extensions to the group by clause that allow you to generate multiple levels of aggregation, subtotals and grand totals in a single query. Rollup is for hierarchical subtotals, while cube generates all possible combinations of subtotals, creating a data cube. Chapter 32: Transactions and Concurrency Control. This chapter explains the principles behind how databases handle transactions and manage simultaneous access by multiple users. ACID properties. A transaction must have 4 key properties, known by the acronym ACID. Atomicity. The transaction is an all-or-nothing operation. It either completes fully, commit, or has no effect at all, rollback. Consistency. The transaction brings the database from one valid state to another. Isolation. Transactions running concurrently should not interfere with each other. The result should be the same as if they were run one after another, serially. Durability. Once a transaction is committed, its changes are permanent and will survive system failures. Concurrency phenomena. When isolation is not perfect, several problems can occur, including dirty reads, non-repeatable reads, and phantoms. Isolation levels. SQL defines several isolation levels that allow a programmer to trade off performance for a stricter guarantee of isolation. The levels are read uncommitted, read committed, repeatable read, and serializable, with serializable being the strictest. Concurrency control methods. Pessimistic concurrency control. This approach assumes that conflicts are likely and uses locks to prevent users from modifying the same data at the same time. Optimistic concurrency control. This approach assumes that conflicts are rare. It allows transactions to work on a private snapshot of the data and then checks for conflicts only at commit time. Chapter 33: Optimizing SQL. The final chapter provides a collection of practical tips for writing more efficient SQL queries. The performance of a query depends heavily on the database system's query optimizer, which can be either rule-based or, more commonly today, cost-based. General tips. Use simple expressions. The optimizer is not always good at algebraic simplification. Avoid expressions on indexed columns in the where clause, as this can prevent the optimizer from using the index. Avoid unnecessary sorting, order by, select distinct, union. Prefer joins over nested subqueries, as the optimizer can often find a better execution plan for a join. Provide the optimizer with extra, but logically redundant, join information. Indexes. Index tables carefully. Too many indexes can slow down insert, update, and delete operations. Understand the difference between a clustered index, which determines the physical order of the data, and a non-clustered index. The order of columns in a multi-column index is very important. Statistics. A cost-based optimizer relies on statistics about the data, e.g., the number of rows, the distribution of values, to make good decisions. It's crucial to keep these statistics up to date, especially after large data modifications. Know your optimizer. Ultimately, the best way to optimize SQL is to understand the specific behavior and hotspots of your particular database system's optimizer and to test different query formulations to see which performs best. That's all for this episode of Geek Capsule. We hope it gave you a fresh perspective on the world of technology. We'd love to hear your thoughts, so feel free to leave a comment or share your feedback. If you enjoyed the show, don't forget to subscribe and join us next time for another essential read. Until then, keep your curiosity sparked and your mind open.